The immense heat emanating from the Sun is an undeniable fact, palpable even without deep scientific inquiry. However, behind this obvious circumstance lies one of astrophysics' greatest puzzles, baffling even the most brilliant minds. Our central star possesses a truly paradoxical characteristic that defies intuitive understanding and, at first glance, even fundamental laws of physics. The solar corona, the outermost and most distant layer of its atmosphere, is immeasurably, astonishingly hotter than the visible surface itself. This means our star is a true inferno, not where its scorching core rages, but significantly higher, in a region where common sense dictates a gradual cooling. To illustrate, the temperature on the Sun's surface, known as the photosphere, only reaches a few thousand degrees Celsius. Yet, in the tenuous corona, these figures soar to a staggering several million degrees Celsius. Despite powerful ground-based telescopes and an extensive fleet of spacecraft tirelessly monitoring this celestial giant's activity for decades, over 100 years of continuous observation have not yielded a definitive answer to the question, what precisely causes such extreme heating of the solar corona? We are about to embark on a fascinating journey into this topic to uncover everything currently known about our star's greatest mystery. As a total solar eclipse approaches, the world transforms. Daylight outside fades, giving way to twilight, as if late evening has arrived, and the air noticeably cools. The sky, where the sun shone brightly just moments before, now displays a captivating spectacle, an absolutely black disk surrounded by a halo of ghostly white luminescence. This fantastic glow is the solar corona, the very outer layer of the sun's atmosphere, composed of incredibly tenuous ionized gas. Its luminosity, compared to the blinding disk of the star, is so faint that for centuries, total solar eclipses remained the only opportunity for astronomers to study this mysterious, and usually hidden part of the sun. It was thanks to these rare celestial phenomena, during the total solar eclipse of 1869, that astronomers made a truly astonishing discovery. While studying the corona's spectrum, they found a mysterious green line that absolutely did not correspond to the spectral fingerprints of any known chemical elements at the time. This led to the hypothesis of coronium, a supposed new, extremely interesting chemical element believed to exist exclusively on the Sun. Scientists, intrigued by this discovery, speculated that coronium must be a light, inert gas, analogous to the already discovered helium. However, despite decades of persistent searching, all attempts to detect traces of this enigmatic element on Earth proved futile. Thus, the concept of coronium persisted in the scientific community for about 70 years before being definitively excluded from scientific literature, as it turned out not to be a new chemical element at all. The true explanation for this mysterious green line only arrived in 1939, when two astrophysicists finally uncovered its secret. They convincingly demonstrated that this emission line was nothing other than the spectral signature of iron, but iron superheated to such incredible temperatures that it had ionized 13 times. This meant that the iron atom had lost half of its electrons due to extreme thermal exposure. And it was at this moment that the grand problem of solar corona heating first emerged in all its acuteness. For when scientists calculated the temperatures required for such deep ionization, they obtained truly astronomical values, on the order of several million degrees Celsius. This turned out to be almost 200 times higher than the temperature on the visible surface of the Sun. Imagine an absurd situation. A person feels unbearable heat from a campfire and decides to move further away. But as they distance themselves from the heat source, the scorching heat only intensifies, becoming more unbearable. Thus, although the strange green emission line baffled scientists for decades in search of an explanation, its solution ultimately led to an even larger and more perplexing astrophysical problem. So, let's start with the deepest layer of the solar atmosphere accessible for direct observation, the photosphere. This is the boiling plasma ocean whose surface is covered with characteristic granules, constantly changing convective cells, each comparable in size to a small country. This visible layer of the Sun is surprisingly thin, its thickness not exceeding 400 kilometers, which allows us to perceive the star's disk as a sharply defined, almost cut-out silhouette. The photosphere traditionally serves as the standard for measuring our star's diameter. Temperatures in this region range from 4,000 to 6,000 degrees Celsius. Directly above the photosphere lies another, even thinner, yet extremely important layer, serving as a bridge between it and the mysterious corona. This is the chromosphere. This region consists of significantly more tenuous ionized gas, which, during total solar eclipses, appears to observers as an elegant, thin, and bright red ring or arc bordering the dark silhouette of the moon. Unlike the sharply defined photosphere, the chromosphere's boundaries are less distinct, and its extent above the star's surface can vary from 400 to 2,000 kilometers. This zone is an arena for extremely turbulent activity, reminiscent in its dynamics of Earth's troposphere, where powerful thunderstorms and atmospheric storms form. In the Sun's chromosphere, colossal plasma storms constantly rage. Here, magnetic field lines, erupting from beneath the surface, release enormous amounts of energy, exciting the plasma. This furious activity manifests as solar filaments and prominences, gigantic, dazzling arches of incandescent plasma that majestically rise through the chromosphere, soaring upwards and reaching the farthest limits of the corona. However, the most characteristic and perhaps most surprising elements of this thin region of the solar atmosphere are the sinuous, hair-like formations known as spicules. They represent another vivid manifestation of twisted magnetic fields that propel plasma upwards in rapid jets. At certain wavelengths, these jets create the impression that the Sun's surface is densely covered with some cosmic grass. The most grandiose spicules can rise to heights of up to 5,000 kilometers from the surface before gravity pulls them back down. And it is here, precisely in the chromosphere, that temperature readings begin to exhibit truly strange, illogical patterns. In the upper part of the photosphere, which smoothly transitions into the chromosphere, the temperature still remains high, around 6,000 degrees Celsius. However, as one moves deeper into the chromosphere, it unexpectedly begins to decrease, dropping to 4,000 degrees Celsius. This, seemingly, is quite consistent with expectations. The further from a powerful energy source, the cooler it gets. But then something completely unpredictable happens. Above this point, the temperature suddenly begins to rise rapidly, reaching an incredible 20,000 degrees Celsius at the very upper boundary of the chromosphere. At such extremely high temperatures, hydrogen actively emits reddish light, which is why during total solar eclipses, the chromospheric ring appears crimson, and the majestic prominences resemble fiery tongues erupting from behind the moon's dark disk. At the same time, even more astonishing phenomena unfold in the transition region located between the chromosphere and the Sun's corona. This atmospheric layer is extremely thin, only about 100 kilometers thick. Can one imagine what this means on the grand scale of our star? Yet, it is precisely here that the temperature shows a rapid increase, reaching and even exceeding 500,000 degrees Celsius. In the lower layers of the corona, temperatures can already reach several million degrees, and during solar flares, they superheat to tens of millions of degrees Celsius. The part of the solar atmosphere commonly called the corona actually begins at an altitude of approximately 2,000 kilometers above the surface and extends millions of kilometers into space. Ultimately, the corona has no distinct boundaries. Instead, it envelopes the entire solar system in the form of the solar wind, a supersonic flow of plasma. Thus, even our own planet is immersed in this extended atmosphere of the Sun. Of course, the second law of thermodynamics rules out the possibility of direct heat transfer from the Sun's internal regions to the corona, since, logically, the temperature should decrease, not increase, with distance from the source. Therefore, non-thermal processes are behind this phenomenon. As is known, temperature is simply a measure of the speed of particle motion. A higher oscillation speed corresponds to a higher temperature, and vice versa. Essentially, the constituent particles of plasma, namely ions, free protons, and electrons, do not slow down as they move away from the Sun. On the contrary, they gain speed. But why does this happen? Undoubtedly, the most obvious accelerator appears to be the Sun's magnetic field, responsible for many curious phenomena we are accustomed to observing. However, the exact mechanism of this acceleration, and why it manifests exclusively in the corona, remains unclear. Over the past 4 decades, physicists dedicated to studying the Sun have put forth a number of hypotheses capable of explaining this anomalous heating. Of the wide variety of proposals, only 2 of these hypotheses remain relevant today. One attributes the heating to known solar flares, but not the powerful events that affect satellites and people sensitive to weather changes, but they're much smaller. Relatives, called nanoflares. The other hypothesis considers so-called waves as the energy carrier to the outer layers. Both of these hypotheses are extremely difficult to verify experimentally. So, to understand what is happening more deeply, it is necessary to reiterate that the Sun is much more than just a ball of incandescent plasma. It is a huge and complex magnet. The Sun's magnetic field is generated by a dynamo mechanism, driven by the star's rotation and the differential rotation speed of its layers, as well as continuous convection, hot material, heated by the hellish heat of nuclear fusion, rises, while colder material, conversely, sinks. It is this constant movement of electrically conductive fluid, which plasma is, that leads to the generation of a magnetic field. What is plasma? It is a state of matter where its atoms effectively break down, forming a mixture of free electrons and ions. It is often called the fourth state of matter, alongside the familiar solid, liquid, and gas. However, perhaps it would be more appropriate to call it even the first state, since most matter in the universe exists in the form of plasma. Although the temperatures and densities required for its existence are beyond our earthly experience, they are, nevertheless, quite common in cosmic space. Now, it is interesting how plasma behaves under various conditions. It can be compared to a liquid or a gas, but with certain additional features related to electromagnetism. Since plasma consists of electrically charged particles, it interacts very actively with a magnetic field and responds sensitively to its changes. Indeed, a significant portion of natural plasma is permeated by magnetic fields, and plasma created in laboratory conditions is held in place by magnetic fields. This is precisely how thermonuclear reactors function. The first person to attempt to combine the mathematical foundations of fluid mechanics and electromagnetism was the Swedish physicist Hannes Alfvén. In 1942, he realized that changes in the magnetic field, manifesting as waves, would affect the plasma, which, in turn, would also respond by generating waves. This phenomenon is often compared to the vibration of a guitar string. In this case, the string represents a magnetic field line, but instead of air around it, there is plasma. Thus, the vibrations of the string, i.e. the magnetic field, will generate waves that propagate along the magnetic field lines. For his theoretical discovery, which was later confirmed by astronomical observations, Alfvén was awarded the Nobel Prize in Physics in 1970, and magnetic waves have since borne his name. So, the Sun's photosphere, as already established, is a dynamic environment that is constantly in turbulent motion due to the convection of matter. And it is this continuous churning that causes disturbances in the star's magnetic field, generating magnetic waves that, in turn, are transmitted to the plasma. But how does this affect the corona, and why does it heat up at all? Well, an important characteristic of Alfvén waves is their ability to carry energy, particularly kinetic energy. Plasma particles, caught by such waves, undergo oscillatory motions, shifting in a direction perpendicular to the magnetic field lines. At the same time, the wave itself propagates along these lines. This creates characteristic disturbances in the plasma that have the potential to transfer energy over significant distances. It is assumed that if the waves dissipate, meaning they die out in a certain way, they must transfer all their energy to the plasma, accelerating the charged particles. It remains only to find out exactly how this scattering and subsequent energy transfer occur. One of the mechanisms considered is called resonant absorption. One can imagine that plasma particles oscillate at their own inherent frequency, and if this frequency harmonizes with the frequency of the Alfvén wave, the wave productively transforms its energy into the energy of the particles. Ions, as if caught by the wave, acquire rapid motion. Another mechanism interprets dissipation through the interference of various Alfvén waves with each other. When different types of waves collide, they can twist, generating turbulence in the plasma, similar to how two streams of water meet. turbulence causes particles to move chaotically, and the organized energy of the waves is converted into accelerated particle motion. There are other wave mechanisms, but resonant scattering is considered one of the main presumed methods of energy transfer. Nevertheless, the wave hypothesis is not exhausted by this alone when it comes to heating the corona to extreme temperatures. The idea of solar flares, or rather, nanoflares, was first proposed in the 1970s by one of the prominent solar researchers, Eugene Parker. Parker argued for additional heating through impulsive energy releases. He hypothesized the existence of miniature versions of solar flares, which are about 1 billion times smaller than ordinary ones, but possess significant energy potential due to their extreme prevalence on the Sun. Despite their smaller size, their mechanism of appearance should be similar to that of ordinary flares, i.e., through a phenomenon called magnetic reconnection. Because solar plasma is continuously moving, magnetic field lines naturally respond to this dynamic, bending and distorting like an elastic band. Like stretched rubber, field lines accumulate magnetic energy, and inevitably this energy must be released. At a critical moment, magnetic fields lose their stability and literally tear at the most vulnerable point. However, the magnetic field lines rapidly reconfigure into a new structure, releasing all the stored potential. This is where plasma heating potentially occurs. At the moment of reconnection, the magnetic field undergoes rapid changes. This rapid change generates an intense electric field, which, of course, affects charged particles, accelerating them along the field lines. The acceleration can be so significant that ions can reach relativistic speeds in a fleeting interval. This is where the fundamental difference between the two heating hypotheses manifests. Alphane waves transmit energy gradually through plasma oscillations, while nanoflares heat it instantly with sudden bursts of energy. If nanoflares indeed occur ubiquitously and with high frequency across the Sun's surface, then collectively they could provide enough energy to maintain the corona's super-high temperature. Nevertheless, the catch is that the true frequency of nanoflares has not yet been determined, and this, unfortunately, is not the only problem with this hypothesis. Ordinary flares generate a wide spectrum of high-energy radiation, but nanoflares emit orders of magnitude less energy, making them extremely difficult to detect. It is no less difficult to register magnetic waves penetrating through plasma, as instruments are required to monitor the extreme ultraviolet region. It is for this reason that the mystery of corona heating remained unanswered for decades. Earth's atmosphere effectively absorbs radiation at these wavelengths. Consequently, even with ground-based telescopes of adequate resolving power, many critically important solar processes remain invisible. Only at the turn of the 1990s and 2000s was the presence of magnetohydrodynamic waves first verified by space observatories such as the European Space Agency's SOHO and NASA's SDO. Incidentally, SOHO, which was designed to operate for 2 years, has continued to study the Sun for 3 decades. It was this spacecraft that first recorded cyclic oscillations of spectral lines, corresponding to relatively slow Alphane waves. In 2011, another spacecraft, SDO, monitored periodic plasma pulsations in the X-ray and ultraviolet ranges, which served as confirmation of the presence of Alphane waves. And in 2023, the discovery of small-scale but high-speed magnetic waves using the Solar Orbiter spacecraft was announced. For now, these studies are at the forefront of heliophysical science, and researchers continue to delve deeper into the phenomenon of magnetohydrodynamic waves. Regarding nanoflares, their study presents even greater difficulty. Physicists suggest that the size of these phenomena does not exceed 100 kilometers, which, of course, is absolutely tiny on the scale of the Sun. Yes, current observational instruments possess impressive resolving power, but even this does not guarantee successful observation. The point is that many diverse events occur on the Sun, and it is very difficult to determine which one correlates with a particular physical process. It is necessary to establish with absolute certainty that the heating of a certain plasma region occurred precisely due to magnetic reconnection, and not for any other reason. Indirect observations have indeed provided some data on the existence of nanoflares, but a comprehensive understanding of their prevalence and the sufficiency of their cumulative energy to explain the phenomenon of solar corona heating is still lacking. Furthermore, it remains unclear whether these microscopic flares can effectively heat the corona specifically, that is, regions significantly distant from the star's surface. This poses a serious problem, as it is known that ordinary solar flares primarily heat their immediate surroundings. The question arises, can the energy released by small flares dissipate into the coronal plasma, or is it directed to other regions? This critically important question remains unresolved. The situation is complicated by the fact that scientists cannot confidently assert that only one of the two possible mechanisms is responsible for the actual heating of the corona. It is quite likely that they act in concert. For example, the process of magnetic reconnection, which causes nanoflares, could well initiate the generation of alpha waves, which, in turn, are capable of further heating the corona. Thus, a pressing question arises about the proportion of energy carried by each of these mechanisms. In addition, the frequency of these processes remains a mystery, as their prediction is extremely difficult in the absence of direct observations. Solar plasma is an extremely complex magnetic turbulent system, and modern computer models inevitably contain simplifications that could be critically important when attempting to describe this volatile and dynamic environment. In other words, the real conditions in the corona differ significantly from model representations. For example, many simulations show that alpha waves can propagate unimpeded through the corona without significant energy loss, which, accordingly, leaves open the question of their ability to dissipate precisely where they are expected to heat. It is clear that the number of unresolved questions is quite significant, and it is no coincidence that this problem is considered one of the most complex in modern astrophysics. Studying the Sun, as is known, is associated with far greater difficulties than studying any of the planets in the solar system. It is not possible to launch a spacecraft into a low orbit around the star to obtain images with the finest detail, as the extreme conditions near the star make this impossible. In fact, the closest approach humanity has achieved was approximately 6 million kilometers, which is equivalent to almost 9 solar radii. This historical milestone was surpassed by the Parker Solar Probe at the end of 2024, when it made its 22nd close approach to the star out of 26 planned. The Parker Solar Probe mission, the first in human history to attempt to approach the Sun and launched in 2018, is a bold step designed to help unravel the many mysteries of our star and gain a deeper understanding of its pervasive influence on the entire solar system. To successfully execute its ambitious scientific program, the solar probe is equipped with a high-tech thermal shield 11.5 centimeters thick. Naturally, the question arises as to what material this shield, capable of withstanding temperatures measured in millions of degrees Celsius, is made of. The answer lies in carbon foam, but not the entire secret is contained within this material. In reality, the seemingly intimidating millions of degrees Celsius are not as catastrophic if one understands the fundamental difference between the concept of temperature and the quantity of heat. Temperature defines the speed of individual particle motion, whereas heat represents the total amount of energy that these particles can transfer. The Sun's corona, especially its distant regions, is an extremely tenuous environment. Consequently, despite the fact that particles within it move at enormous speeds, their concentration is too low to transfer a significant amount of energy, i.e., heat, to the probe. The actual temperature that the surface of the Parker probe experiences is estimated to be approximately 1,400 degrees Celsius. This is, undoubtedly, a high temperature, but not so critical that the thermal shield cannot cope with it. At the same time, the spacecraft itself, protected by the shield, operates in relatively comfortable temperatures not exceeding 30 degrees Celsius. Among the vast array of data already transmitted by the probe to Earth, S-shaped magnetic field bends, which the spacecraft recorded by the hundreds and even thousands simultaneously during its first close approach to the Sun, are of particular interest. These bends, called switchbacks, briefly change the direction of the magnetic field and have generated significant interest among the scientific community. In the context of the global problem of corona heating, such a powerful S-shaped bend can accumulate a significant amount of magnetic energy, which can then be released into the surrounding plasma when these switchbacks straighten. It is logical to assume that this released energy must go somewhere, and why shouldn't it be responsible for the observed heating of the corona? Scientists continue to meticulously analyze the acquired data, seeking to understand how and in which regions these bends form, as well as precisely where their energy is transferred. Observations are ongoing, and the Parker Solar Probe mission is greatly expanding our knowledge of the Sun notably. By diving almost to the very bottom of the solar system's gravitational well, the spacecraft achieves an incredible speed, reaching approximately 700,000 kilometers per hour. Thus, the Parker Solar Probe is not only the closest spacecraft to the Sun but also the fastest probe in human history.